We're going to talk about the normal distribution. But before we do that, I just want to go back and talk about density curves for a minute. I talked about density curves when we were talking about visualizing the distribution of one quantitative variable. It's basically a smooth way to visualize a variable's distribution. And one thing that I don't think I said at the time is that the total area under a density curve is 1. And the handy thing about that is if you want to know what percent of the population is above or below a certain interval, you can just look for the area of that interval. So remember my movie data. I have a plot here where I've put both the histogram, so we've binned it into those bins, and also the density plot onto the same plot. You can kind of see how the density plot is a smoothed out version of the histogram. You can see the little bumps happening wherever there are some bars. And the area under this curve, so this gray area that we can see defined here, I'll just box it out a little bit, that area is 1. And so if I wanted to know what proportion of movies made between $500 million, which I think is here, and $1 billion, $1,000 million, is that a billion? If I wanted to know what proportion of movies made between that amount of money, I could just look for this area. And we could estimate it if we wanted to just by looking at this. I would probably estimate that that's like, I don't know, 15%. It's a small percentage, and I can tell because I'm looking at the whole area and then trying to see what the area of that small chunk would be. So this is a density curve for a real distribution, the distribution of world box office totals. But then there are all these theoretical distributions that mathematicians and statisticians have thought up and have defined very carefully with mathematics. And these distributions have special shapes, and they also have names. So I'm pretty sure that this is the F distribution, and this one is the chi-square distribution. And you can see that both of those distributions are skewed. They're skewed to the right. I think I've got the normal distribution here, and I think this is the t distribution. And both of these are nice symmetric distributions. But there are many, many other named distributions. And there aren't really things in the real world that make these perfect distributions, but they have nice properties, and so mathematicians and statisticians like them because they're easy to prove things about. So the normal distribution is probably the most famous theoretical distribution. It's a symmetric, bell-shaped distribution. So we're going to be using the normal distribution more as the class goes on to help us approximate things. And when you are using a normal distribution, you want to be able to tell people which version of the normal distribution you're talking about. So if we were on the phone and I was trying to describe a normal distribution to you, I'd need to tell you what the mean was, where it's centered, and probably the standard deviation, so you'd know how spread out it was. Instead of trying to say, it goes up a little bit and it's around this number, and then it goes up even more and it gets steeper, right? It would be easier if I could just tell you the two numbers, the mean and the standard deviation, and then you would know things about the way that normal distributions look, so you could figure out which one I was talking about. So we will denote a normal distribution like this. So we'll say x, that's a variable, follows, so the squiggly line we read as follows. X follows a normal distribution with mean, mu, and standard deviation, sigma. So if we were thinking about a normal distribution like this, let me give us a little baseline here to work with. We would think about the center of that distribution being at mu, and then we could go out one standard deviation. This would be mu plus sigma, mu minus sigma. I could go out mu plus 2 sigma and mu minus 2 sigma, and that would be how the distribution would work.